Sir Gilbert Walker was actually a mathematician, physicist, and he was an officer of the East India Company in India during the late 19th century, early 20th century, and he was concerned about the famines over India, and he wanted to figure out whether they can be predicted or understood better. So he took all the pressure data he could get from islands, so Tahiti and Darwin, and he figured out that there was this oscillation which he called Southern Oscillation, and realized that the negative phase of it tended to be associated with the droughts over India, and of course famines are not the same thing as droughts, but he tried to use that information to relate the large-scale pressure oscillations with the monsoon droughts. That sat there from the 1920s. Only in the 1960s people began to realize that actually this is related to the so-called El Nino, that the Southern Oscillation and El Nino are not entirely different, and the idea of the feedbacks that are in the pressure oscillation and the ocean's role and the coupled processes is typically attributed to Jakob Bjerknes, but Peter here makes a point that it was Troop who was already on this track, but that's kind of the way history works. Some people tend to get attention, but Bjerknes was not aware of Troop's work, so he just followed up his own analysis and reported what we now call a Bjerknes feedback that we will see later on. So the early depictions of the Walker circulation, Troop said, for simplicity, we shall consider that there is a single drift of most importance in the upper troposphere, and that this flows from the negative area of the Southern Oscillation, and hence anomalously low surface pressure across the Pacific to its central and eastern regions. So you're going from the West Pacific towards the central and eastern regions. It's compensated by a return flow near the surface from the eastern Pacific to the negative area. So you have this perturbed Walker cell with the upper level divergence and lower level convergence. This is a component of the frictional ageostrophic flow between high pressure over the eastern Pacific and low pressure over the negative area, negative in the sense of below average sea level pressure associated with the warm temperatures. There is descent in this circulation over the central eastern Pacific and ascent over the negative area and adjacent regions, and a toroidal circulation in the vertical zonal plane is set up. Okay, so that's our Walker cell. So this is what he had in mind. So we are looking at schematic representation of the Walker circulation based on Julian Chervin's paper, but basically encapsulating Troop's idea and confirming his ideas initially reported in 1961 and 1965. We have seen this before in other ways, but this is just showing the pressure coordinate and the circulations. This is 200 and 850 hectopascal at 4 stations. So very little data was used to draw these maps. So you have convergence. The arrows here show the departures from average. So you have asymmetry there, as you can see, right, also above, but you have convergence and rising motion that we talked about, and drift towards the eastern high pressure, and then sinking motion or subsidence. You have the other half on this side and on this side that we already talked about. So you have sinking motion or the cold high pressure of the East Pacific, rising air over the warm West Pacific, which shifts around on El Nino timescales, as you can see here. So it has significantly changed here. So now you have anomalously warm temperatures here and anomalously low sea level pressure, anomalously cold temperatures and anomalously high sea level pressure, and divergence here and convergence here. So these are anomalous divergence and convergence, and again you have the asymmetry. So depending on how strong the warm event is, the El Nino, this shift and the strength of the cold anomalies and warm anomalies will be very different, as we will see. Okay, and based on that strength also the teleconnections or remote impacts of El Nino will also be different. For example, on the Indian monsoon. This is something we had also seen in chapter 1. We are looking at seasonal latitudinal mean, so 5 south 5 north mean longitudinal cells, looking at Africa, Borneo, and I think this is the Cold Tongue, some island, I hope, well, maybe just ABC. So this is DJF, and here we were mostly talking about the seasonal shifts that happen. So JJA, when you have ITCZ to the north, the OLR is underneath. You can see in shades, and SSTs are there as well. And you can see the SST and STCZ differences that we talked about before during DJF. So the entire system shifts back and forth and changes in strength as well. And it has impacts on the Indian Ocean side and the Atlantic side as well, as you would expect if the entire diabatic heating is moving back and forth. Okay, so this is, I think, the difference of no, this is at 90 east, so this is at the equator, sorry, this is at 25 north, and so the seasonal differences are here. At 25 north here you have mostly the Asian monsoon Mayu Bayu front impact, and here you have the Indian monsoon impact during June, July, August, which is very different during the winter months. So the meridional differences in the zonal circulations is obvious based on the heating. So we'll look at the nature of the zonal circulations in the next podcast to say why this large scale Walker cell doesn't have to worry about the weak temperature gradient assumption we needed to deal with the 10 to the 6 meter scale perturbations that had to be explained in terms of the baroclinic processes, vertical motion, and how the lower level and the upper level were communicating. Remember the Charney's conundrum of how to produce baroclinic processes in the baroclinic structure of the tropics at 10 to the 6 meter scale. But Walker cell is at 10 to the 7, so it doesn't need this weak temperature gradient approximation. Okay.